Hello everyone. So in this particular video, we are going to see the working principle of transformer and its phasor diagram. Actually, it is a very basic questions that can be asked in any of the interviews. And regarding this particular questions, there are many resources available in internets and books and all. But in this particular video, I'll quickly summarize the important points that you need to mention during this explanation. Like what are the assumptions you are taking while you are explaining the working principle of transformers and the phasor diagrams. Okay, so let me tell you what are the assumptions we are going to consider in this particular analysis. So assumptions will be, first of all, I'll be considering the ideal conditions. So the my winding resistances and all are zero. So primary winding resistance and secondary winding resistance are simply zero, and the leakage reactance of the primary circuit and secondary circuit, these two are also zero. Okay, these two are also zero. And the core loss of the transformer core is also zero. Okay, there is no hysteresis associated with the BH curve. These are the assumptions, and also I'm assuming like my core of the transformer has linear BH curve. Okay, so linear BH curve, if you have the linear BH curve with you, so this is your B and H. I'm assuming it has a linear BH curve. Linear BH curve means permeability of the core is constant. Okay, constant, and it is a fixed value. So these are the assumptions that I will consider. People actually consider the reluctance of the core as a zero also, like infinite permeability. If you consider core permeability as infinity, then reluctance offered by the core will be zero. Okay, people consider this also, but I will summarize. Maybe I will add this particular case at the last, but as of now let me focus on the I have a core that has finite permeability or constant permeability. That because of that I will be getting a constant reluctance of the core, or the finite reluctance of the core. Okay, so let me raise these points. And first I will be considering no load conditions. Okay, so let me consider no load condition. No load condition means the secondary side is simply open circuited. That your I2 current is simply zero. Okay. Now let me focus on the working principle. In the primary side, you have Vs of t, which is a sinusoid signal, and we have this N1 number of turns in the primary circuit, and your primary is something. It is a kind of a closed circuit. Okay, so this closed circuit will demand a current that is I E of t. I am denoting it as I of t. It is exciting current, and this I of t is flowing through the N1 number of turns. So that will produce a MMF. I am calling that MMF as a F. So that is N1 into IE of t. Okay, this is the MMF that the primary winding will produce, you can say. And one more thing I have to add here, the basic working principle of transformer is basically based on the Faraday's law of electromagnetic inductions. What is that electromagnetic inductions process? Although you are aware of, but let me add few points regarding that. Let's say you have a coil that has n number of turns, and that coil is affecting by some change of flux phi of t. So this coil will produce a voltage, some, let's say it is E, that will be n d phi of d phi by dt. Okay, and if you consider the minus sign, so this minus sign will simply represent the effect will oppose its cause of creation. So just a quick recap: if there is any n number of turns, and that turns is affected by change of flux phi of t, that coil will induce a voltage, and this is how the magnitude of the induced voltage will be n d phi by dt. And if you consider the Lenz law, it will have a minus sign with it. Okay, so this is just a quick recap, you can say, of the Faraday law of electronic induction. Now the moment you have this MMF with you, and you also have core that has reluctance, so this particular MMF will produce a flux in the core. That flux phi of t will be MMF by reluctance. So N1 I of t by reluctance. So this is your flux, and this particular flux is flowing through the core. So it will induce voltage in the primary circuit. So that is something called, I'm calling it as E1, and same flux is flowing through the secondary circuit also. So it will induce a voltage E2 here. Okay. Now at no load there will no current, but still you will be having induced voltage, because there is no relationship in between the induced voltage and the open circuit. Okay. So still you will be having induced voltage in the secondary circuit, and this is the flux you are getting. So let's say I am assuming the flux that is flowing through the core, it is a sinusoidal quantity. I am assuming the core flux, maybe it is something phi of t is equals to phi m sine omega t. It is my core flux. Okay. If I am considering that this is my steady state flux of the core, what will be the induced voltage at the primary circuit? That is nothing but E1. Maybe I can say it is a small E1 n d phi of d phi by dt. Now, in this particular equation, let's say uh, I consider the Lenz law, Lenz effect also. So for that, I need to give minus sign here, and this minus sign will basically represent the effect will oppose its cause of creation. So by this particular notation, I am trying to say whatever voltage will get induced in the primary side, that will oppose the flow of current through the primary coil, such that the flux production in the core reduces, and the voltage don't even get induced in the coil. Okay, so the polarity of the voltage, or E1, should be in such a way that it can oppose the all the entire effect. So you can do, there are two ways to do that. Let's say you basically assigning a polarity here, plus minus of this particular E1, and also this is the polarity of the supply voltage, plus and minus. So the moment you are assigning this plus minus polarity at the induced voltage of the induced voltage, you are basically saying that the moment you have this plus minus polarity, this current will get simply reduced, this I of t will simply get reduced, and it will try to oppose its cause of creation. So that is why we have to, either you have to mark this plus minus symbol at the figure, or you have to directly consider the effect in the equation itself. So as of now, let's say I am not considering this plus minus symbol here. I am just considering, okay, there will be induced voltage in the primary coil. Rather, I am considering the Lenz effect or Lenz law in the equation itself to calculate the induced EMF. So both are the same scenario. Either you can mark the plus minus symbol here, and you need not to even consider this negative sign. Okay, this is the case. Or you can simply remove the signs from here, and you can add that opposite or do you say the effect of Lenz law in the equation itself. So if you consider here, you will get minus n1. So it is your n1 phi m omega cos omega t. Okay, so this is how you will get, and this is nothing but n phi m omega sin omega t minus pi by 2. Okay, so this is the two case, you can say, two equations. So if I consider this phi of t as a reference phasor, okay, let's say this is my phi of t as a reference phasor. Okay, and my E of t or E1 of t, it is lagging by 90 degrees. See, it is lagging by 90-degree electrical. Okay, so it will lag by 90 degree, and it is E1, and depending on the turns ratio, your E2 will also be decided, like, okay. So see here, in case of this high of t is flowing throughout the core, so you will get induced voltage E2 also, right? So let me write down the E2 also here. E2 will be N2 d phi by dt, and it will be N2 phi m omega uh, cos omega t. See, we will see the polarity of these induced voltages and all in the case number 2 at loaded condition. But as of now, I'm just focusing only on the magnitude. Okay, and these two magnitudes are in the same phase basically. These two are in the same phase. So here you will be having E2, you can say, and your core has this finite reluctance, and because of that you are getting this exciting current, and it will be in phase. Okay, it will be in phase with the phi of t. So this is your I of t. Why it will be in phase? Because phi of t is nothing but n1 I of t by reluctance. If you see this particular equation, your n1 and r1 are constant, and IET and phi it is just they are you can say that they are directly proportional. So that is why your phi t and IET will be in phase. Okay. And one more thing here, if you look at the primary circuit, your VST and E1 they are in the opposite polarity and nature, and that I have considered with like that effect I have considered here with the minus sign. So to show that opposite polarity of the induced voltage, you can say, so I'll be having here it is a minus E1, and this is also my supply voltage Vs, you can say. So here you can see I am showing that my supply voltage and the induced voltage polarity are opposite. Okay, so this will be my phasor diagram at no load condition. Now we will see the on load condition. Okay, so let's say you have now on load condition. Now you have a load connected at the secondary side. Okay, you have connected the load at a secondary terminal, that is ZL, and let's say it is the current that is flowing, that is I2, and it has N2 number of turns, it has N1 number of turns. The induced voltage E1 here and induced voltage here E2 here. We will see the polarity of this induced voltage, and here phi of t is flowing. Now tell me one thing, the moment you are closing the switch, a current I2 will flow because of the induced voltage. Okay, but still we don't know what will be the polarity of the induced voltage and how the current will flow. Now the current is flowing, and why current is flowing? Because of the closed circuit, and in the closed circuit the current can only flow if there is any voltage or voltage source is there in the circuit. So if I try to draw here the secondary circuit, I have some coil here, and I have my this load resistance, load impedance, you can say ZL. It is inducing some voltage E2, and because of the closed circuit I am getting this current I2. Okay, so what Lenz law says? Lenz law says my effect will always oppose its cause of creation. So the current will flow in the secondary circuit in such a way that it can oppose the flow of this flux phi t, because the main culprit of this particular case is phi of t. If there is no phi of t, there will not be any voltage induced, there will not be any current and all. Okay, so according to Lenz law, effect should always oppose its cause of creation. So my current I2t, this I2t current will flow in the secondary circuit in such a way that it can oppose the flow of phi t. So that means my secondary circuit should produce a flux in the upward direction. If it is an upward direction, they can basically cancel each other, right? So it can only happen if the current is flowing in this manner, like in this manner. If your current direction is in this way, then your flux will produce in the upward direction, and these two will be in opposing nature. Okay, and if you see this particular current direction, if my I2 is flowing through the ZL, it is simply plus and it is simply minus. So basically your plus polarity will come here and negative polarity will come here. So this is how the polarity will get induced in case of on loaded condition. So this is the, you can say, the entire scenario. You'll be having current, that current will oppose the main core flux and all. But there is something more that also we need to discuss. Okay, now we are aware of how this voltage will get induced, the current flow and all. Now let me tell you one more thing. The moment you have this opposing nature flux, it is basically reducing the total core flux. Then what will be the case? The case is, if you see, uh, let's say you have this Vs, and which is also equals to E1, and which is nothing but N d phi by dt. Okay. Now at steady state, all of these quantities are same. Now at transient moment, you can say this particular flux, maybe I'm calling it as a phi 2. It is phi 2 to of t. It is, they're opposing each other. Phi of t and phi 2 t, they're opposing each other. So that will reduce the flux. Now, but this particular equation is saying my this phi of t must be constant, like at, okay, it is time varying, but it should be constant. Maybe phi of t sine omega t. It should not be varying. Okay, at some moment it is phi t is equals to phi m sine omega t. Another moment it will be phi of t is equal to 2 phi m sine omega t. So this is that will not be the case, right? What I'm saying, because of this opposite polarity of flux, there should not be the case like your core flux will reduce and you are getting two different fluxes at or many different fluxes at different instants. So that will not be the case, because your source voltage is constant. So to get the source voltage constant, your phi of t also needs to be constant. If my phi of t was initially phi m sine omega t, even if there is any counter flux coming in the system, this particular quantity must remain same. And how this must particular quantity will be same? We have to draw a current from primary side. We have to draw current from primary side, some extra current, maybe it is I2 prime. That extra current will produce a flux in the you can say that extra current will produce MMF in the primary coil, and that primary coil MMF will produce a flux. Maybe that is something called phi 2 prime, and this phi 2 prime and this phi 2 will cancel each other, and such that you will be having only phi of t in the core. So it will fulfill the all of your requirements. Okay, so this is how the actual scenario will happen. Let me explain you one more time. Let me erase these things and all. Now the moment you have the current in the secondary circuit, this current will flow through the N2 number of turns, and there is a MMF, that is that we can call it as a F2 MMF. This F2 MMF will produce a flux, that is something I'm calling it as a phi 2. Okay, and as per Lenz law, this phi 2 will oppose the phi of t, the main flux. So these two, like the phi of t and phi 2 of t, they will oppose each other, and these two, the effect will reduce the main flux from phi of t to, the main core flux will reduce phi of t to phi of t minus phi 2 of t. So this is how the scenario will go, like your core flux will reduce. But if you see this particular equation, this equation, as per this equation, if your Vs is constant, your E1 must be constant, and this phi of t also needs to be constant at steady state. But because of the loading condition of the secondary, it is saying there is a reduction in the core flux. So what will happen to satisfy this particular condition? My supply will provide another extra current. Maybe I'm calling that flux, the current that will be, maybe I can use some different color. That current will be I2 prime. Okay, this I2 prime current will flow through the N1 turns, and that N1 and I2 prime current will produce a MMF. Maybe so that is something F2 prime. and thus F2 prime will produce a flux that will be phi 2 of t, and this phi 2 of t will basically try to aid the main flux. So what will be what will happen after getting extra amount of current from the source? My core flux is something like this. Initially the core flux was phi of t. Because of secondary current I am getting phi 2 of t, and again because of the primary additional current I am also getting another flux, that is phi 2 of t, and it should be in such a way that it can cancel uh, the secondary flux. So see, this two will cancel and I'll be having only phi of t. So this is how your flux will maintain at steady state, even though there is a loading in the secondary circuit. Now what will be the you can say the phasor diagram. So you have this flux phi of t, you have this E2, sorry, it is your E1, and let's say this is your E2, and this is was your IE, the exciting current, and let's say my load is lagging, so this will be my I2, and this was my you can say supply voltage, okay, and my I2, this current I2 and this current I2 prime must be opposing in nature to nullify the effect of flux created by the secondary circuit. So to show that one, I have to draw current I2 prime in opposite direction. So this is my I2 prime, and these two current will produce a resultant current. So that will something we call it as a primary current I1. So this is my power load power factor theta 2, and this is my input power factor theta 1. Okay, so this will be your phasor diagram under the loaded condition. So I explained what was the assumptions before I start this kind of explanation, what are the scenario that will happen in at no load condition, and what will happen at loaded conditions. Okay, so this transient phenomena, you can say it is very important how the primary is you can say pumping the extra current into the transformer to maintain the same flux to fulfill this particular equation. It is a very good equation actually. You have to remember, you can say, this particular equation. So and this is the phasor diagram, you can say, at steady states and all. Okay, I hope now it is clear. Still, if you have any doubt regarding the working principle, you can ask me in the chat. Thank you.